Welcome to this video that aims to introduce phylogenetics for linguistics. I am Annemarie Verkerk from Saarland University in Germany. I teach and do research there on linguistic typology and related topics such as language change, including phylogenetics. This is a short lecture that introduces phylogenetics, the quantitative analysis of genealogical structure, especially for linguists. So we will go over what historical linguistics is. We'll go over the history of quantitative approaches to phylogenetic tree building in linguistics. We'll look at contemporary quantitative approaches, which are mostly character-based, and we will look at some very few practicalities, further application, and there is some advice at the end of the lecture. This is the starting point of today's lecture. It is that languages change all the time. They change from generation to generation. I am sure that you can think of ways the way you talk or your grammar differs from the ways your grandparents used their languages, the languages that they spoke. They also change within one speaker's lifetime. I'm equally sure that you can think of ways in which the languages that you speak have changed from when you were a child, for example. In addition, at least half of the world's population is multilingual, often from an early age onwards. This means that languages change because of multilingual skills across speaker populations. This is sometimes called context-induced language change. But languages, of course, also change because of reasons that have nothing to do with language contact. And these are sometimes called internal causes. This sets the stage for what's so interesting about language change, and where do we study language change? Well, we study it in historical linguistics. So historical linguistics is the study of language change. More precisely, it describes the changes that have taken place in a set of related languages and accounts for them both in terms of prehistorical and historical events, and most importantly, in terms of general linguistic processes. And these can be phonological, morphological, and syntactic. In the right corner, you see the cover of a handbook of historical linguistics by Lyle Campbell. This is what I'm going to use for the next couple of slides to introduce to you what historical linguistics is all about, and then later on how all of that relates to phylogenetics. At the bottom, you see the academic fields that interact with historical linguistics. Historical linguistics is not concerned with the history of linguistics, but it should be noted that historical linguistics has played an important role in the development of linguistics. So basically, linguistics started out only as historical linguistics in the 19th century. And then it took a major turn when people like de Saussure started focusing on contemporary languages. Before, basically, people only cared or seemed to care about historical languages, or languages that were no longer spoken. In addition, one of the central methods of historical linguistics, the comparative method, which we'll talk about later, is seen as one of the major scientific achievements of the 19th century. The origin of language is a topic which is not generally considered to be part of traditional historical linguistics. This is the question how modern-day language could have evolved from, for example, non-human primate call systems, or gestures, or music, or whatever. But there is a lot of work on the origin of language since the 2000s, and historical linguistics is very relevant for research in this field. But the origin of language remains not something that traditional historical linguists concern themselves with. Finally, historical linguistics is also not about determining what correct language use is. The linguistic term for that is prescriptivism. Historical linguistics really don't care about people's opinion about language change. They accept it as the course of nature. In fact, if languages wouldn't change, they would be out of jobs. Historical linguistics is biased towards Indo-European and European languages. This is not noticeable actually at all in Campbell's book, but if you go outside of that, you will definitely notice that. So Indo-European is the language family to which English, French, Russian, but also Persian and Hindi belong. And it's special in the sense that many historical languages that belong to that family have been preserved, right? They have been preserved in writing. These include Latin, Ancient Greek, Sanskrit, and so on. And this makes historical analysis of the Indo-European languages of the Indo-European language family particularly interesting. So let's start with looking what historical linguistics is all about? What are some central themes? First up, the types of things that change. So first of all, sound change. Sound change happens all the time. Historical linguistics are especially interested in regular sound change. So here we have an example where Spanish, this is a Romance language, has originally a P in certain words, and this changed to a B in intervocalic position. So if you want to read more about all of these kind of details, you should really consult a Campbell's handbook. So this example means that in this context between vowels, every original P, so the ancestral P, before Spanish became contemporary Spanish, became a B. It's not the case that some original intervocalic P's became B's in some words, but became K's in other words and Sh's in other words, right, in unpredictable ways. And these types of regularity that we observe in sound change is really the bread and butter of historical linguistics. It's really very important. Then we have morphological change. So here the example is the English suffix "eth." We can think about the words "bereath," for example, that Campbell has in his example. This was once upon a time, well, not so long ago, in the Middle Ages, the third person singular verb agreement suffix in English, and it was replaced in time by "se" or "s," right? So instead of "giveth" or "bereath," we now have "betrayed" or "gives." Then we have syntactic change. We have, for example, the fact that English has SVO word order, right? Subjects come before verbs and verbs come before objects. But for example, Dutch and German have SVO word order in main clauses, but they have SOV word order in subordinate clauses. So we know that there must have been changes there. This is syntactic change. Then lexical change. Here we have a very modern example. We have a word. The word app that we use for the applications on our phones is a clipping, morphological clipping from application, right? So we have different words come into our languages all the time via different processes. The processes themselves are often described in morphology, but studying lexical change is really a core business of historical linguistics. Then we have semantic change. The textbook example here is the words hound versus dog in English. So hound is cognate to German Hund and Dutch Hond, but and once upon a time in English was used to refer to any type of dog, right? But over the centuries, the meaning of hound in English narrowed until it was only used for dogs that are involved in hunting. And dog has become the general term for the concept dog in English. So this is an instance of semantic change. Another major theme in historical linguistics that we should talk about are the processes through which languages change. These can be split into internal versus external change. That's kind of what I started with earlier on. So Campbell describes the internal causes of language change as rooted in communication, right? So on what we humans are able to distinguish with our hearing, or what we are able to process with our cognitive makeup and our biology, our limitations on control of our speech organs. So that's where internal causes of that's where causes for internal changes can be found. So the change from p to b in Spanish in between vowels is an example of this type of internal change, and you can read about this in Campbell if you can. Then we also have grammaticalization. This is another internal process. This is centrally concerned with the evolution of grammatical forms, in a sense that these often derive from words or morphemes that do not have a grammatical use. An example here is the English infinitive marker to, right? It originally, and still does, it indicates a goal, right? As in the sentence, I'm walking to university. But as an infinitive marker, for example, in the sentence, the child wants to play, it only has a grammatical function, namely to mark the verb as infinitive. External change can be said to be rooted for some part in a social evaluation. I'm sure you can think of many examples here, especially regarding semantic change, where words underwent certain changes and people no longer wanted to use them for certain reasons. But a major external cause of change in linguistics is language contact. That means speakers of one language community are in contact with speakers of another language community, and this can have consequences for the languages involved on all levels, right? One aspect that stands out, even to lay people, is borrowing, the transfer of linguistic material from one language to another. And this concerns especially loanwords, like English computer, that has been borrowed into many of the world's languages. This brings us to models. A central finding, but also now a given, is that languages are historically related to other languages. I already preempted that idea earlier on. So I already mentioned that Indo-European, the family to which English, French, Russian, but also Persian and Hindi belong, they are all genealogically related, which means that they descend, with changes of course, from a common ancestor. So there's two major models of historical relationships between languages. These are the family tree model and the wave model. The tree model posits that languages originate when a community that speaks a shared language breaks up and no longer talks to each other. The languages will then gradually change and become differentiated, much like a family tree that you might list your mom and your dad and your grandparents and so on and so on. So a pedigree, in a way. This is the same structure. So the tree model has the same structure as a family pedigree. Above you see one of the oldest examples of a family tree. This is one of the Slavic family by Silaskovsky. It splits up the family in an eastern and western branch, as you can see. The wave theory rather states that innovations, so things that are new in language, spread out from the center in which they first emerge, and depending on how extensive their spread is, they reach few or many languages. The example on this slide here is from Francois 2015, where each event of a language change defines its own isogloss. So this is an isogloss is here a line on the graphic. So this is a continuous zone circled by a line, all planted onto a map. This displays that the innovation originated somewhere and then diffused across dialects or languages. In a linguistic continuum characterized by mutual intelligibility, so dialects where people can understand each other even if they are from different speech communities, the normal situation is for these isoglosses to intersect basically all the time. So in the picture here, E and F, we can call them language E and F, they share an isogloss, but E also shares an isogloss with C and D. F also shares an isogloss with G, and then there's also one rather big one in green where we have an isogloss which covers E, F, G, and H. What is often the output of applying these models is basically linguistic classification, right? In terms of family trees, or in the case of an application of wave theory, in terms of dialect change, or sometimes in terms of discussion of language areas. Language family trees are established groups of languages that are genealogically related. In other words, they are all descended from the same ancestor. There are very many of these. So Glottolog on the inserted picture here says there are 430. But when you watch this and visit Glottolog, the number might be different. That is because sometimes linguists decide that two families are one family after all, or they decide that a chunk of an established family actually, in terms of more recent evidence, isn't actually part of that family. So more distant genetic relationships are also proposed and tested, sometimes falsified, at other times corroborated. Finally, we get to methods. How do historical linguists do all of this? And when is she finally going to talk about phylogenetics? Well, the word is there on the slide. I'll quickly talk about the comparative method because it is so central to historical linguistics and phylogenetics, and then we'll move to phylogenetics. Quickly, I want to talk really quickly about this mention on the slide that you have there, computer-assisted methods. As we will see, the comparative method and phylogenetics deals with cognates. These are genealogically related words. And if you're dealing with a lot of words and languages, things basically grow out of hand. There is a lot of data that you then are using for historical analysis. Therefore, you can choose to let the computer help you. There is a good introduction and tutorial on this by Mattis List and colleagues that you will find in the references. Then, The last method listed there, I will quickly mention it, but we are not going to come back to it. This is linguistic paleontology. It's the study of history and prehistory on the basis of reconstructed vocabulary and its reconstructed meanings. For example, what life was like for the Proto-Indo-Europeans, the speakers of the ancestral language of this family to which all of these languages belong, like English, French, Russian, Persian, Hindi, right? So linguistic paleontology deals with all aspects of life, including reconstructed terms for flora and fauna, but also going beyond that, looking at society, politics, religion, culture, etc. But now quickly about the comparative method. So the comparative method deals with sets of genealogically related words or morphemes called cognates and analyzes these in terms of sound correspondences such that proto-words can be reconstructed. Ultimately, we know exactly how words or morphemes have changed from the proto-language to the present day. We can then also try to reconstruct meanings of those proto-words, and we can also basically try to reconstruct other parts of the proto-language, such as its sound inventory. So Campbell has a long chapter on this where he details these 7 steps with a lot of exercises for you to do if you are so inclined. But maybe for understanding it in full, you really need an example. So this is an example. These are numerals listed in several Indo-European languages. In the first column, we have the meanings of these number words, right? So we have 1, 2, 3, all the way to 100. Then we have a column which is labeled pi. This stands for Proto-Indo-European. This is the ancestor of the Indo-European languages. Then in the remaining columns, we have different parts of the Indo-European family represented. The first is Anatolian, then we have words from Sanskrit, Greek, Latin, and Lithuanian. And all of these words that you see in italics are cognates, right? So they are descendants from Proto-Indo-European to these languages and ultimately to their descendants as well. When we look at these and other sets of cognates long enough, we discover certain patterns. These are correspondences between sounds that are due to regular sound change, right? I was talking about the importance of regular sound change earlier. So this is the main example that you have here. You can eyeball it a little bit, but I'll give you one hint here. So for the numerals 6 and 7, Greek has h, right, has an h there, where all the others have an s sound. And the s sound is also reconstructed in Proto-Indo-European. So the Proto-Indo-European forms are all prefixed with an asterisk, which means that these are reconstructed forms on the basis of contemporary and historical language evidence. And this is the kind of analysis that historical linguistics engages in. So we are going to move to phylogenetics from here, but first we have to make an outing to the first time when linguists have taken place in the quantitative computational approach to studying language change. The first time was namely through the work of Morris Swadesh, who developed this idea that linguistic relations between two languages can be measured by the amount of shared cognates that pair has. So how did that work? Swadesh compiled word lists of related languages. These lists are now known as Swadesh lists because he was the first to do it, right? And then he determined genealogical distance between languages on the basis of the proportion of words that are not cognates in each pair of languages. Swadesh lists are highly frequent and generally thought to be well conserved and not prone to be borrowed. This is important because the cognacy of the words is the measure that determines the extent to which any pair of languages is related in Swadesh's approach. The table is an example of what such a set of cognate-coded Swadesh lists from different languages might look like. There is a set of 4 meanings, and the basic, most frequent words for these meanings in 4 languages has been given. In numbers behind each word, these denote the cognate classes. For instance, in the first column, the Russian and Lithuanian words for run belong to cognate class 3. That means they belong to the same cognate class, they are related. Whereas the French and the Dutch word for run belong to different cognate classes 1 and 2. Swadesh calculated the distance between each pair of languages by dividing the number of words which are not cognate by the total number of cognates. This is the distance between the language pair. For example, in the table on top, French and Dutch share only one cognate term, that for bottom, so there are 3 terms which are not cognate. So the distance between French and Dutch in the distance table is 0.75, and of course one would typically use a large list of meanings in order to best describe the distances. These distance tables were then processed using clustering algorithms, creating subgroups of various sizes. Then Swadesh discovered that on average, after 1,000 years have passed, languages retain about 80% of the highly conserved basic vocabulary material compared to their ancestral ancient languages. Here we have a range of language pairs that were studied. So in each case, in green, you have the more ancient pair, and then you have the more ancient language and the more recent language in brown, and then on the right you have what percentage of basic vocabulary has been retained and how much that is per 1,000 years. This enabled Swadesh to develop the idea behind grottochronology. Grottochronology is the notion that we can date language splits as cognate material is being lost at a steady rate of 80% every 1,000 years. They could now infer on the basis of the percentage of cognates shared how long a specific language had been evolving since it had split up from its ancestor. In the late 60s, 70s, and 80s, however, lexicostatistics and glottochronology was discredited and abandoned. There were a range of critiques. The first being that the method did not allow for any incorporation of other relations aside from splitting relations. So the method only allowed for classifications in forms of trees rather than waves or networks, even if results were rarely presented in the tree format. So this is a critique that has come back again and again. It also has modern phylogenetic analysis has also faced this critique. Then there were issues with the data. It was difficult to decide between synonyms in Swadesh lists. Critics were also concerned about the impact of undetected loanwords on the classification. But most importantly, several independent studies pointed out that the rate of lexical displacement is not stable across all lexical items or meanings, across all languages and across all periods in time. So this universal rate of 80% retention that Swadesh found was essentially falsified, most importantly also by Bergsland and Vogt in 1962. And because of the failure of this work to develop further, for several decades mainstream linguists did not engage in any form of computational estimates of language family relations, be it time related, so chronology related, be it subgrouping related, nothing. There were, of course, some analysis of this still happening, but they were not mainstream at all. However, of course, historical linguists have not been the only ones that have been looking at changing systems that are passed on from generation to generation. Biological species are, of course, the most common and well-studied examples of entities that change with modification over generations, and whose evolution can be described by the tree model. And while linguists wanted nothing to do with quantitative approaches after Swadesh and his colleagues were discredited, evolutionary biologists were making enormous advances, and a range of different methods was proposed and being used to build phylogenetic trees and to study the evolution of species traits on these trees. So the tree of the primate order on the right was compiled in 1995, almost 20 years ago. By that time, there were already over 100 already existing phylogenetic estimates of the primate phylogeny. So it is quite clear to see how much of an advantage the biologists have over us when it comes to quantitative assessment of historical relationships between entities, in their case species, in our case languages. And at the turn of the century, these same methods, so these methods from evolutionary biology, became used for the first time for linguistics, and also for the second time since Swadesh. Linguists have since then started to employ computational methods to infer language family relationships. The first study to do so was Gray and Jordan in 2000. They used cognate-coded lexical material from 77 languages to build an Austronesian tree. And then since then, in the last 24 years, a plethora of linguistic family trees have been constructed using this set of computational tools borrowed from evolutionary biology. These are just a few out of many similar papers, and these are all a bit older by now, but if you If you look on Google Scholar, you will find a lot of these. So how does phylogenetics work, right? The key paper for you to read is called Language Phylogenies. It's by Michael Dunn in 2014 from the Routledge Handbook of Historical Linguistics that you see in the top right corner. And this is a very interesting book on historical linguistics, especially for those of you that are interested in the connections that historical linguistics has to other disciplines, such as archaeology and genetics. In any case, the main split between methods for inferring phylogenies for creating quantitative estimates of family trees is between so-called distance-based methods and character-based methods. We're going to come back to that in a second and explore a little bit what data analysis looks like for these types of analyses. So in his paper, Dunn stresses the importance of high-quality data, regardless of methods. And what data for phylogenetic inference look like, you already kind of know from the previous parts of this video. So you already know about cognates from the historical linguistics part, and you already know about Swadesh lists from the part when I talked about those, right? So words for various meanings or concepts are collected. Here in table 1, these are meaning 1 and meaning 2. The corresponding lexemes in 4 languages are listed. Here we have language A, B, C, and D, and they are coded for cognate class membership. That means that the words for meaning 1 in language A and B are cognate because they belong to the same class, class A. For meaning 1, there is also another cognate class, B, etc. For language D, there is no entry, and there's also no cognate class listed there. So for phylogenetic inference, the cognate classes are made binary, such that ultimately we create a binary column for each cognate set in the table. This can be observed in Dunn's table 2. So thinking back about meaning 1 in language A and B, you can see that there's now a column in our table 2 called column 1A, for which language A and language B both have 1, right? Language C has a 0 there because it actually has a word that belongs to a different cognate class 1B. And language D has a question mark because there is no data for that language. As an example of a distance-based method, right? So we're moving from data to trees really quickly. I have put Rama and Colacina's 2013 UPGMA tree of Dravidian to the right. So let's explain this a little bit. Dravidian is a smaller family native to the Indian subcontinent. It has approximately 80 languages, but the most well-described ones are there's about 20 or 30 of them that are pretty well described. So Rama and Colacina use a distance-based technique called UPGMA, which constructs a rooted tree, which you can also think of as a dendrogram, that reflects the structure present in a pairwise similarity matrix. So one step from table 2 that we just saw to a similarity matrix would be again calculating, for example, the amount of shared cognates between pairs of languages. At each step, then, it takes the similarity matrix and the nearest 2 clusters are combined into a higher level cluster. Can also be calculated without cognate analysis, but rather by calculating the phonetic semblance of pairs of words across languages. This is often done in dialectometry, so there's definitely a role for distance-based phylogenetic methods in linguistics, and you can read more about this in the paper by Dunn, 2014. More popular, however, are so-called character-based methods. I'm going to give a long quote from Dunn, 2014, that illustrates the difference between distance versus character methods really well. He writes, an alternative family of approaches to phylogenetic inference, known as character-based models of change, estimate the relationship between 2 languages by inferring the pathway by which each evolved from their common ancestor. The difference between 2 languages according to a distance model is always equal to or less than the difference according to a character-based model. Another way of looking at this is that the distance between 2 languages is the shortest path from one another. A character-based model is constrained to provide an evolutionarily plausible pathway to each language from their inferred common ancestor And this is almost always a longer pathway than the shortest distance for turning one language into another. The shortcuts that distance methods take are more serious the further back in time the common ancestor is located. Character-based methods are therefore more realistic models of evolutionary processes. So a very quick summary here. Distance-based methods are good for data sets of closely related languages such as dialects, become increasingly unreliable as languages are less closely related. Therefore, the example that I showed earlier is one of a few that, so there's very little distance-based analysis of entire language families that have an ancient history. Rather, for bigger language families, so for Dravidian, but also for other medium-sized and bigger language families, people tend to use character-based methods. These infer evolutionary pathways rather than distances. They go beyond lexicostatistics by implementing variable rates models. So we do not have to hold on to the idea that there is one fixed rate of language change. Oftentimes, these character-based models are implemented using Bayesian methods. And Bayesian maximum likelihood implementations offer a choice of different models and parameter settings to acquire the best fit to the data. So how do character-based methods work? Here I rely on a tutorial to Indo-European Phylogenetics by Goldstein from 2020. This is a great tutorial because it starts by explaining in detail likelihood. This is a key concept. It's important because the most commonly applied character-based methods are so-called maximum likelihood methods. But I don't have time for that in this video, so please look at Goldstein's tutorial, and for now we work with a layman's concept of likelihood, right? Namely that some things are more likely to happen than others, right? And the key idea here is that we can measure likelihood. Goldstein applies likelihood to phylogenetics, the idea being that maximum likelihood phylogenetic estimation identifies the best trees on the basis of an optimality criterion. The optimal tree, or the optimal trees, is the one or are those that make the observed data most likely. Let's say that we want to compare the following two trees. Language A is 0, language B is 1, language C is 0. Goldstein keeps this example simple by stipulating ancestral states and by only taking account of tree topology and not of other parameters such as branch length. But already we have to take into account two important assumptions in this calculation. The diachrony of different sites on a given tree is independent from other places on that same tree, and the diachrony of different lineages is independent. So assumption 1 means that the probability of the value of one character is not affected by the value of another character. So our toy example involves only one character, so this assumption doesn't play a role now, but it is an assumption of the maximum likelihood estimates that you will encounter in a real life example where we have multiple meanings that we are investigating, or well, that we are using as data for our phylogenetic inference analysis, and of course many different cognate classes. Assumption 2 says that the way in which a character develops in one branch is not dependent on the way it develops in another branch. So calculating likelihood proceeds like this. So we can calculate the probability of the observed language data as a product of probabilities. The P is shorthand for the probability of. So the probability of the proto-language of ABC to be 1 is the probability that our character X has the value 1 at the root node proto-ABC. So the probability of X proto-AB is 1, given the X proto-ABC is 1, denotes a conditional probability. That is the probability that our character has the value 1 in proto-AB, given that it was 1 in proto-ABC, right? And we can continue that for the entire formula and verbalize the information that's there. But basically, this is about probabilities of ancestral states and probabilities of nodes and leaves in the tree. So leaves being the languages C, E, and B themselves, and the only node we have in the tree is proto-A and B. We work with them on the basis of what they look like in the ancestral languages. So these are all the probabilities that you need to calculate the likelihood of these two trees, giving rise to the data, right? So the data still being that A is 0, C is 0, and B is 1. So to compute the probabilities in the example, we need a transition model. Transition models in biology are probabilistic models of trait evolution and detail probabilities in the change of a state. It is possible to encode a range of properties of linguistic change in a model, such as variable base frequencies, variable rates of change, variable transition probabilities, but we are going to keep things simple. Goldstein in his tutorial only covers the base frequency and transition probabilities. So the base frequency is the probability of each state, so this is either 0 or 1, at the root of the tree, in our example, proto A, B, and C. And additionally, we need transition probabilities. These are the probabilities of change between the states. In this case, we have one from 0 to 1 and one from 1 to 0. So the transition probabilities are both in I there in the window you have in the bottom left. They relate the probability of a change of state, right? P1 to 0 and P0 to 1. And in II, the probability of no change of state, where the P where you stay 0 is 0.8 and the P where you stay 1 is 0.8. This gives rise to a transition probability matrix. Once you have that transition probability matrix and you have the probability of each state at the root of the tree, you can calculate the trees. You can calculate the likelihood of each tree that we just saw. So that's what I've kind of tried to summarize here in one slide. We have hypothetical tree 1, hypothetical tree 2, we have the transition probabilities, and then we have the calculations, the likelihoods and the log likelihoods. So because likelihoods get so small, we typically log them so that they become a little bit bigger and a bit more easy to understand. The probability of the character data is therefore higher given hypothetical tree 2 compared to hypothetical tree 1. As the calculations reveal, this is because tree 2 involves fewer change events that lower the likelihood. Were we to continue trying different typologies, we would eventually identify the tree that makes the data most likely. And this is a very, very simplified illustration of maximum likelihood estimation. In practice, maximum likelihood computation is much more complex, for it takes into account factors such as branch length, rate variation among characters, and so on. In addition, we usually do not know the ancestral states of characters, so this would be another probability that we are calculating on the basis of observed data across alternative ancestral state scenarios. But this gives you a basic understanding of how maximum likelihood computation works in phylogenetic inference. So summarizing here a little bit and switching to black, because we're going to talk about Bayesian stuff, and therefore you need to shift your brain around a little bit. So now we have white on black. So to summarize here, the maximum likelihood approach tries to explain a set of data, D, by quantifying how likely it has been to have been produced by a hypothesized process or mechanism, which is H. The likelihood L is thus the probability P to see the observed data under a proposed mechanism H. As before, the data consists of Swadesh lists of cognate data, which I'm only illustrating with a snippet of data here. The model of evolutionary change captures the results of a tree generation mechanism, so it contains a fully specified tree proposal as well as other parameters. These parameters assess the probability of cognate changes, so either cognate losses or emergence of new cognate sets, right? So this is about changes from 0 to 1, as we just saw. These parameters together are the hypothesis that we are testing, and the likelihood of this hypothesis, having generated the data D, is assessed through the likelihood score assigned to each hypothesis. So we can have a range of methods to generate different trees, different models of evolutionary change in which all the parameters are specified, which I'll come to in a second. But the main idea of the likelihood approach is that for each of these proposed hypotheses, so for each of these bundles of parameters that are specified in the model of evolutionary change that is generated, their likelihood of generating the data is assessed by a likelihood score, so that ultimately then analysis can return those hypotheses about trees that have high likelihood scores. Let's imagine that we wanted to compute likelihood by hand, as we just did for Goldstein's very short, but very small trees, right? So his trees only had 3 languages in them, one internal node and one ancestral language. It was just about manageable to push that all onto one slide. But what happens when you have more languages that you want to study, right? So typically, people want to study language families with, I don't know, up to 100, well, no, up to 1400 languages, which is Atlantic Congo. This is a graph that Felsenstein created. It's the number of rooted trees with n-labeled tips and with unlabeled interior nodes. The illustration that he wants to make here is that the number of all trees that are possible given a set of language or a set of species increases. I think it's not just exponentially, it just increases like mad, right? So we have for 22 languages there at the bottom of the slide, we have an insane number of trees that we will want to look at. Calculating the likelihood of all of those trees is, first of all, a heavy computational task, but it's also unfeasible for other reasons. Because most of the trees that we would be able to, well, most of the trees that are possible, right, are uninteresting. They won't include, so we will have a lot of trees there which do not have high likelihoods of generating the data. We do not actually want to assess all the possible rooted bifurcating trees. We want to get to the trees that have high likelihoods. So we want to get to the trees that have such model parameters that they are most likely to have generated the observed data. And this number is just way too high. We don't want to assess all the trees. We want to assess only the most likely trees. And the solution for doing that is Bayesian Monte Carlo Markov chain sampling. Bayesian MCMC methods search the tree space for the region of highest likelihood. And it does this by starting at a random point first. So this random point is a tree proposal. So we have a topology, we have an internal grouping of languages, we have branch length, which are really important, and we have, and associated with those parameters, we have a likelihood score, right? Then the next thing that will happen is the MCMC chain will move to a new place by randomly perturbing the parameters of the tree, generating a new set of values, parameter values. If the new parameter values have a higher likelihood, it will always move to this new position in the tree space defined by those parameters, like this. So the idea is that the chain of proposed tree parameters climbs higher and higher in terms of likelihood. You can think of the space in which this chain is located as a two-dimensional landscape, where we aim to find the mountain with the highest likelihood values. Since only accepting higher likelihood parameter proposals would imply we could get stuck at a low optimum, like a small hill, instead of the peak of the mountain that we need to find, sets of parameters with lower likelihoods may also be accepted, depending on how much lower they are. So if the likelihood difference is very large, like this one, and the proposed set of values has a much lower likelihood, the chain disregards this proposal and a new set of values is generated, like this. However, parameter sets that do not represent a too large drop in likelihood may be accepted. And so the chain goes on and on. This process is repeated for millions of so-called iterations of new parameter proposals. Typically every 1000 steps, the proposed tree parameters and likelihood values are saved to a posterior sample. The initial part of the chain, which contains low likelihood proposals, is disregarded, and one is left with a posterior tree sample of typically ranging from a few hundred to 1,000 trees. The posterior sample contains more or less equally highly likely set of tree parameters, so those tree topologies, branch lengths, and transition probabilities that have the highest probability of having generated the data. This sample of hundreds of trees can then be summarized to a so-called consensus tree. These are the figures that we encounter in publications, even though in these days we also encounter many figures that have been generated by density tree, which captures uncertainty in the estimation, especially of the tree structure itself. So to summarize, we can use Bayesian Monte Carlo Markov chain sampling to search the tree space for the region of highest likelihood, given the data and the model of evolutionary change. What you get out is a posterior sample of models that are scored for their probability of generating the data. Of course, there is a lot to say about models of evolutionary change, and this is where you really have to get into the nitty-gritty bits of things and in various other ways. So I'm going to spend very little time on this today. So one of the things that people have concerned themselves with is the data type. So I've been talking so far about lexical cognate data, right? These are made binary, and this is what's used in most studies of linguistic phylogenies. But you can imagine, for example, that genetic data and multi-state data require different models. You can also imagine, as some have done, that there can be studies, phylogenetic studies, of data that's not lexical. This is called oftentimes structural data, where people take typological parameters and estimate trees on the basis of those. So this is one thing to look for in your search for more information on this topic. Then we have a clock model. The clock model is about the rate of change. Can it, if it has to be constant throughout the entire tree, that means that you have a strict clock. If you have a relaxed clock, that means that the rate of change is allowed to vary in different parts of the tree. Then we have to talk about transition probabilities, and this is central for change with regard to the cognates within their cognate sets. In a one-rate model, a single parameter q expresses the probability that a character state 1 will turn into 0 or vice versa. So basically, in a one-rate model, the chance of losing a cognate is the same as gaining one. In a two-rate model, the probability that 1 will turn into 0, so q1 0, is estimated separately from the probability that 1 will turn into 0. So here the probabilities for losing cognates and creating new ones is separated from one another. Then we have the gamma model. This assumes that each character belongs to one of a specified number of rate classes. Each cognate set belongs to a class, hence capturing stable and less stable meanings in terms of items of vocabulary. So we can imagine that, for example, numerals, as we saw before in the example of Indo-European, are really stable and change very, very slowly, whereas some other meanings or concepts might change a little bit faster, and the gamma model captures this kind of rate variation. Then we have under the covariant model, where the rate of each character is allowed to vary along the branches of the tree, and the stochastic dollar model captures a key feature of real cognate histories. That is, a cognate set may only be innovated once in the data set. One parameter governs the distribution of rates of cognate sets arising in the data, and another the distribution of rates of loss of their reflexes. If you want to know more, there is a good paper by Greenhill et al. 2020, and there's also a talk on YouTube, Bayesian Phylogenetic Linguistics, that I recommend for more details and for more information about different types of analysis, but also more details specifically about Bayesian linguistics. So ultimately, almost at the end of this lecture, we come to why do we care about trees? Why is this so interesting? Why is it interesting to study language families from a computational perspective? And in part, of course, this is about subgrouping, language relations, traditional goals of historical linguistics. I want to exemplify this a little bit with this very recent paper called Language Trees with Sampled Ancestors Support a Hybrid Model for the Origin of Indo-European Languages. And this paper is, well, for me currently speaking, one of the last stations in a very long journey where quantitative linguists have tried to estimate what the Indo-European family has looked like over time. And this has been a matter of great controversy that you can also read up more upon, and you can also watch several things on YouTube for that. If you YouTube something like Origin of Indo-European Languages, you'll find a lot of related material. What has been a central question here in this set of studies is where Proto-Indo-European was spoken and when it was spoken. And with these quantitative analyses, we can shed light on these histories, right? When you look at this tree in the top left, you can see that there is a lot of uncertainty with regard to the backbone of the Indo-European tree. You can infer that there are certain events that we can connect to the origin of the Indo-European family, and we can also infer that there is a certain time associated with that has to be of a certain depth. So definitely, quantitative historical linguistics, estimating language phylogenies, is really relevant not just for looking at subgroupings, not just for looking at, okay, do these languages belong to a single family or not, which is actually something that you do inside of historical linguistics and not so much in phylogenetics. But there are ways to also go beyond just inferring phylogenies, but talking about times and places that are actually at the direct interest of traditional historical linguistics as well. So that's summarized a little bit on this slide. So point 1 here, we are interested with doing this kind of stuff. Also, additionally, in the direction and order of evolutionary change, looking at homelands, looking at spatial migration patterns of families. We are interested in the nature of evolutionary processes, expansions, borrowing, punctuations, how tree-like evolution has been. And we are interested in dating divergence events. We're interested in population splits and feature divergence. 3 evolutionary processes on this list have to do with the language family itself in a way. They have to do with how this family moves through space, how it moves through time, and what the essential process of diversification really is. The second 3 evolutionary processes don't have so much to do with the tree itself and with the language family itself, but with linguistic features that we can model onto phylogenetic trees. I want to start with a quick quote here from Pagel 97 on what we can do with phylogenies. And he writes there, coupled with data on the characteristics, behaviors, and lifestyles of species, phylogenies can be used to infer the historical evolutionary processes that must have existed in the past, given the patterns of diversity seen in the present. Comparative statistical methods can be used to discover, in a manner that might be described as statistical paleontology, the nature of the evolutionary processes as they advanced along what would become the branches of the phylogenetic tree. So when it comes to typological investigations, we can partake in point 4, 5, and 6 on this list. It becomes possible to infer character states, so to perform this kind of virtual archaeology. We can also model correlations between features, so for example, looking at word order dependencies, while at the same time modeling interdependencies between languages that are due to the fact that they are related to one another. We can model these at the same time and do this properly in a statistic accurate fashion. We can also look at rates of evolution, so we can look at rates of typological change, or the speed at which words are gained or words are lost. This is all very interesting for a typologist such as myself. So I would like to end this lecture by this short example here. Let's say we have 6 languages here. There are 4 yellow languages and 2 blue languages. We can again take the example of word order. So yellow can be SVO, these are languages like English, with the verb in the middle between the subject and the object. And the blue languages are SOV languages like Japanese with the verb at the end. Now we might have a lot to say about this distribution of languages. We can say, if this was a comprehensive sample, we can say, okay, there are 2/3 of the languages are SVO and another third are SOV. But there's a lot of other things that we can say as well if we know a little bit more about history. For example, if the tree that generated these data looked like this, we can infer that there is one change from SVO to SOV. If the tree that generated these data if the tree that corresponds to how these languages are related looks like this, we have instead an ancestral blue language with a change from blue to yellow. And you can of course imagine that for this kind of toy example with 6 languages, that's really not so interesting, right? But just imagine that you had a world tree of all languages, or even just a big family like Atlantic Congo or Austronesian or Indo-European. And these types of inferences about when changes are happening, what proto-languages look like, these are really interesting. And especially when we then couple that to a second trait that somehow relates to word order, right? So you can see that once you scale this up to anything beyond a toy example, it's really relevant to use phylogenetic trees to do typology as well. This is just a kind of a summary slide here, right? If we know the phylogeny of how languages are related, we can model that along with our ideas about how change is happening in typological data and come up with really cool answers to cool questions. So I've reached the end of this lecture on phylogenetics for linguists. I've gone over what historical linguistics is. We've gone over a little bit of history of quantitative approaches to phylogenetic tree building in linguistics. I mean, the central takeaway there is that just as in evolutionary biology, it's kind of an accident of history that these methods were not created by linguists, right? But that it was biologists that did that, because both disciplines are equally interested in history and in modeling this history. Then we talked about contemporary quantitative approaches, mostly about character-based approaches, and had one slide on practicalities and a very limited amount of information on further applications. But please do have a look at the references for further interesting ideas for you to explore. I hope that I have conveyed that there is this inherent link between historical linguistics and phylogenetics. So to apply phylogenetics properly for linguists, the comparative method is essential. Many aspects of how historical linguists have worked for centuries are simply essential. And we hope that as we go into the future and build better models of language change for phylogenetic study, we can deal also better with ideas that historical linguistics have about how languages change. So there's lots of opportunity to work together and to build a true quantitative approach to historical linguistics through phylogenetics. I'm going to end with a reference slide. Thank you very much for your attention, and goodbye.